morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I am going to discuss about polymer composites. It's in Unit 5, so Module 5 of our syllabus. So, coming to the first, the introduction to the composites. Now, these composites, they can be defined as the materials that consist of two or more chemically and physically different phases, which are separated by a distinct interface. So, composites, they are generally made up of two or more materials, and they are physically and chemically distinct. They are separate from each other, and we can see the interface between the two phases while seeing from a microscope, or they can be defined as any multiple phase material which consists of two or more physical or chemical phases which are with the interface separating them. So, they do not form a bonding between each other. Now, here I am showing what exactly are composites. The composites, they are made up of two parts. The first part is the matrix, which forms the outermost part, and the second one is the reinforcement material, which we fill inside the matrix, which provide the strength and hardness to the composite materials. Now, these matrix, it can be of thermoplastic or thermosetting. Now, here the thermoplastic that we are going to use are nylon, all polypropylene or PET or ABS or PC or PP or PPS. There are different types of thermoplastics that we can use. Similarly, we can use different types of thermosetting polymers. For example, polyester, polyvinyl ester, epoxy resin or phenolic groups we can use as the matrix. And the reinforcement material which we are going to add inside the matrix can be either glass, or they can be aromatic amides, or they can be carbon, or they can be natural fibers. So, the matrix is the one which binds the reinforced material, and it do not let this reinforced material to come in contact with the environment. That means, the matrix, it protects the reinforcement material, and together they bind to form the composites. Now, most primitive man-made composite materials, they were the straws and mud, and they are going to combine together to form the bricks, and they ultimately form the building material. So, here I am showing the straw and the muds, and these are the conventional composites having a layer of the rubber, and then they have two layers of the woven cotton fabric. Now, the composites, they can also be natural polymer composites. Now, the natural polymer, it includes the collagen, it includes the fibers made of the collagen molecules, then there is the fiber arrays formed from it, ultimately there is osteons and the bone. So, some of the examples which we can use as natural polymer composites are the wood or the cotton or the hemp or the soya bean, wheat and corn. Now, these composite materials, they are the materials which are composed of two or more distinct phases. As I have already discussed, one phase is the matrix phase and the other phase is the disperse phase, and they have bulk properties which are significantly different from those of any of the constituents. So, when these two bind together to form the composite, then the properties of the composite is going to be significantly different from the matrix as well as from the disperse phase. Now, coming first to the matrix phase. Now this matrix phase, it is a continuous material which is constituent and it encloses the composite and give its bulk form. So as I have already said, this matrix phase, it is going to bind the disperse or the reinforcing phase, and it will act as a binding material and it will give it the bulk form. So the matrix, it is usually more ductile and less hard phase, and it holds the disperse phase and it shares a load with it. By saying this shares a load with it, I want to say that when we apply pressure on the composite material, the pressure is taken by the matrix phase, and this matrix phase, it evenly distributes the pressure to the disperse phase. Second is the disperse phase or the reinforcing phase. It is embedded in the matrix in a discontinuous form. It may be continuous or it may be discontinuous. Then it forms the structural constituent of the composite material, which determines the internal structure of the composite. If we use metallic fibers, then different form of strength is going to attain by the composite material. If we use glass fibers or aromatic amides, then the strength of the composite material is going to vary. Now, the disperse phase, it is usually stronger than the matrix phase. So, matrix phase is only the binding material, but actual strength of the composite material, it comes from the disperse phase. Now, here I am taking the example, the composites, polymer matrix composites. Sorry. Now, these are very common and they are the types like polyesters or vinyl esters if I am going to use. Here another example which I have taken of the styrene that we are going to use as the polymer matrix composite. Now, the materials which are used in composites, there can be different materials which we can use in the composites. The first one is the fibers. Fibers are something which have long length to diameter ratio. They are long filamentous structure, and these fibers, they can be made up of glass or the carbon fibers or the polyethylene fibers or the aramid fibers. And depending upon the material that we are going to use, the properties and the strength of the composite material will vary. Second is the resins. The resins that we can use can be either be thermosetting resins or the thermoplastic resins. So, the thermosetting resins are the polyesters which we can use, and the thermoplastic, they can be polyolefins, they can be polyamides, they can be polyphenylene. And there are certain additives which we can add like some filters or the pigments. Now, there are certain advantages of the composite materials. Why we want to use the composite materials? These composite materials, they have higher specific strength than metals, non-metals and even alloys. Strength wise, these composite materials, they have higher strength than all these materials, and their weight is lower than these materials. So, they have been changing, there has been a process of change of using the composite instead of metals or the non-metals or even the alloys. Then they have lower specific gravity in general. Then they have improved stiffness of the material. The material is stiff enough, that means it can withstand high pressure and temperature. These composites, they maintain their weight even at elevated temperatures. That means we can use them at higher temperatures. Therefore, they are being used in the aeronautical industries. Then their toughness is improved we have already discussed that they are made up of matrix and the reinforced material, and the matrix, it evenly distributes the pressure to the reinforced material. Therefore, the toughness of these materials is quite improved than the metals or the non-metals or the alloys. Then the fabrication or the production is cheaper. We are using polymer material, we are using glass fibers or the carbon fibers. They are obviously much more cheaper than the metals. Then their creep and fatigue strength is better. We can use these materials over a long period of time. So these materials, they do not get tired. So they are fatigue resistant materials. Then there can be controlled electrical conductivity is possible. We can control the electrical conductivity. And metals, they are prone to corrosion. So these materials which are covered by the polymeric material from outside, they are corrosion and oxidation resistant. So coming on to the classification based on the different matrices that we are going to use. Here the composite materials, the matrix that we are going to use, on the basis of the different matrix that we use, they can be classified into the polymer matrix composites. If you are using polymer, then they can be classified as the metal matrix composite, and they can be classified as the ceramic matrix composites. And further, the polymer matrix composites, they can be classified as the thermosetting, as the thermoplastics, as the rubber. Now this is our example of resin matrix. Here I am showing the different reinforcement materials that we can use. Here is the particle reinforcement. We can use the metallic particles dispersed in the matrix phase. Then there can be continuous fibers, long fibers can be used. Then we can use the discontinuous fibers or the whiskers. Whiskers are elongated material having pointed edges. Then we can use different particles. Then different fabrics can be used as reinforcement materials. Next, particulate reinforcement composites. Now these particulates, they are harder and they are stiffer than the matrix material. So in the matrix material, if we add small particles of the metal, so they form the particulates. Obviously they are going to be harder and stiffer than the outer matrix material. Now these particulates, they can be of macro, micro or nanoscopic scale, and the improvement of the mechanical behavior depends on the interface bonding. So how good is the strength? It depends upon the bonding between the matrix and the reinforced material. For example, there can be silica epoxy composites, there can be ceramates, there can be concretes, there can be alumina particle reinforced matrix. So different types of particulate reinforced composites can be made. Next is the fiber orientations in fiber reinforced composites. Now these fibers, they can be arranged in a continuous manner and they can be aligned with each other, or these fibers can be shorter in length, that means they are discontinuous, and they are aligned fibers, they are aligned in a particular direction. And the third type can be that these fibers, they are discontinuous, and along with being discontinuous, they are randomly oriented fibers. So our strength of the composite is going to vary with the orientation of the fiber material. Here the fibers, they are continuous and they are aligned. That means they are going to provide full strength to the composite material. Here we can see that breakage is in between the fibers, therefore, the strength of this type of composite material is going to be less. And in the third case, here the fibers, they are discontinuous and they are randomly oriented. In this case, again the strength of the material or the composite is going to be lesser. Now, continuous and aligned. The fibers, they are longer than a critical length, which is the minimum length necessary, such as the entire load is transmitted from the matrix to the fibers. If they are shorter than this critical length, only some of the load is transferred from the matrix to the reinforced material. Fibers lengths greater than 15 times the critical length are considered optimal. So, those fibers we can use where the critical length is greater than the 15 times than the length we require. They are considered as the optimal use. Then the aligned and the continuous fibers, they give the most effective strengthening to the fiber composites. I have already discussed, if the fibers, they are elongated and if they are aligned, then they are going to provide the maximum strength to the composite material rather than the random fibers. Now, in this case, when the fibers, they are discontinuous and aligned, here the fibers, they are shorter than the critical length which is required. Hence, the discontinuous fibers, they are less effective in strengthening the material. However, their composite modulus and tensile strength can approach 50 to 90% of their continuous and aligned counterparts. So, still they can provide strength to the composite material, and they are cheaper, they are faster and easier to fabricate. Obviously, if we need lesser alignment, then we can quickly make this type of composite materials, and they are easy to fabricate into complicated shapes. Then finally, coming to the random, this is also called discrete fibers or the chopped fibers. The strength will not be high like the aligned fibers, but the advantage of using this type of material is it will be isotropic and cheaper. By saying isotropic, I mean the properties of this fiber or this material in all direction is going to be same, and they are obviously going to be cheaper. Now, the next type is the structural composites. A structural composites consists of both homogeneous and composite material. So, the properties of this type of material depends on the characteristic properties of the constituent materials as well as the geometric design. So, structural composites, here the properties are going to depend upon the material that we are using as well as what design we are going to use. These structural composites, they are of two types, laminar composites and another one is the sandwich panel. Now, in the case of laminar composites, it consists of panels of sheets which are two-dimensional. Here you can see the thin sheets which are there in case of laminar composites, and these thin sheets, they are two-dimensional, and these panels, they possess preferred directions to achieve high strength. So, these panels are going to possess the preferred direction, they are going to be aligned in a preferred direction so that we can achieve high strength. Here I am showing the successively oriented layers, they are stacked one above the other and in a preferred direction. Here you can see they are stacked one over the other in a particular direction, and then they are cemented. And such arrangement or the orientation, it is going to ensure the varying the highest with respect to the successive layer involved in the material. The highest strength will be with the successive layer involved in the material. The next type is the sandwich panel. Now, in this case, as you can see, we have sandwiched between the two layers. So, the sandwich panel is also a kind of layered composite, and it consists of faces and core. So, with increasing thickness of the core, its stiffness is also going to increase, as we can see in a common sandwich panel, which is the honeycomb panel. So, on increasing the thickness, the strength of the material will also increase. And the faces, they are formed by two strong outer sheets. So, this sheet and the lower sheet, they are going to form the faces of the sandwich panel. And the core, it is a layer of less dense material. This is the core which is present, and it is less dense than the two faces which are present in the sandwich panel. And the honeycomb structure, it is a structure which contains thin foils forming interlocked hexagonal cells with their axes oriented at right angles in the direction of a face. So, a honeycomb panel is being formed. Next is the fiber reinforced composites, and the mechanical properties of fiber reinforced composites, they depend on the properties of the fiber that we are going to use and degree to which an applied load is transmitted to the fibers by the matrix phase, how much load is being transferred from matrix to the reinforced phase, and there should be good interfacial bond between fiber and matrix. If this interfacial bond is not going to be strong, then on applying pressure, both the phases are going to separate from each other, and the strength of the composite material will decrease. So, depending on the matrix material, these fiber reinforced composites, they are divided into different categories. They can be polymer matrix composites, they can be metal matrix composites, or they can be ceramic matrix composites. Coming first to the polymer matrix composites. It consists of polymer resin as a matrix, and it is being used in the greatest diversity and largest quantities because it is cheap, it is easy to make. The glass fiber reinforced polymer composites, they are produced in the largest quantities, and they can be carbon fiber reinforced polymer composites. They are high performance composites because carbon, we know, it provides good strength to the material. Then they can be aramid fibers. Aramid fibers are the aromatic amide fibers reinforced polymer composites. Here we can use Kevlar, and you know that the Kevlar, it has high strength. So, aramid fiber composites, they possess good strength, they possess high modulus and high impact resistance composites. So, they are high impact resistance composites. Next is the glass fiber reinforced polymer composites. So, here the glass fiber, it is easy to manufacture and it shows good chemical resistance. And these glass fiber surface, they are coated with a thin polymer layer, that is, it is a size to protect the fiber surface from damage. So, the glass fibers, they are coated with the polymeric layer, and these glass fiber reinforced polymer composites, they are used at a temperature below 200 degrees centigrade due to the polymer matrix, because we know that polymers, they are less resistant towards the temperature. And the major application of this glass fiber reinforced composite, it is used in the automotive industry, in the marine vehicles, it is used in the pipes, it is used in the storage containers, it is used in the industrial flooring. Next is the carbon fiber reinforced polymer. Now, these carbon fiber reinforced polymers, they possess high specific modulus, and their specific strength is maintained even at a high temperature. Again, they possess good physical and mechanical properties. Obviously, carbon we are using, so it possesses good physical and mechanical properties. They are expensive while manufacturing, and the organic precursors we can use are the rayon, polyacrylonitrile and pitch. And the diameter of these carbon fiber reinforced polymers, they can vary from 4 to 10 micrometer, and they are coated with epoxy resin to improve the adhesion with matrix so that they can stick properly with the matrix. And the major application of this polymer, it is in the aircraft industries. We prepare aircraft structural components, then you can make sporting goods, then we can prepare rocket motor cases and the pressure vessels. So, there are number of applications of these carbon fiber reinforced polymers. Now, coming to the advantages of polymer composites. Polymer composites, they possess high strength, they are very stiff, they are fracture resistant, they do not break down easily. Then they are good abrasion resistance, that means their surface will not vary with time, the surface is smooth like the way we are going to use it. Then they are good impact resistance, they are good corrosion resistance because we are using the polymeric material as the matrix, therefore they are good corrosion resistance. They are good fatigue resistance, that means they do not get tired easily, and obviously they are low in cost, they are light in weight. So, these all are the advantages of the polymer composites. Applications, we can use these polymer composites in the automobile industries, we can use them in the marine industries like the shafts, like the hulls of the ships, like the spars, and we can use in the aeronautical applications like the components of the rockets, of the aircrafts, of the missiles. Then we can also use these composites in communication antenna, in the electronic circuit boards, and finally we can use them in the safety equipment like in the use of airbags in the cars. Thank you.